Welcome everyone. In this video, we will study the blueprint of algorithm design. When we solve a problem using a computer, we are not only writing code, we are also choosing a strategy. That strategy decides how the problem will be broken down, how the solution will be built, how much memory will be used, and how fast the algorithm will run. This topic is important because the same problem can often be solved in many different ways. Some solutions are simple but slow, some are more complex but much faster. Some use more memory to save time, others save memory but may take longer. Today, we will look at three major ideas. First, how algorithms are classified. Second, how we measure their efficiency using complexity. And third, how important design paradigms such as divide and conquer, dynamic programming, and greedy algorithms help us solve real computational problems. By the end of this video, you should be able to understand not only what an algorithm does, but also why one algorithm may be better than another. This slide shows the algorithmic universe divided into three major classification areas. The first classification is by implementation. This means we look at how the algorithm is written or executed. For example, an algorithm may be recursive. A recursive algorithm calls itself again and again until it reaches a stopping condition. Another implementation style is logical, where the algorithm is expressed using logic and control rules. We can also classify algorithms as serial or parallel. A serial algorithm performs one instruction after another, while a parallel algorithm performs multiple operations at the same time. Finally, an algorithm may be deterministic or non-deterministic. A deterministic algorithm gives the same output every time for the same input. A non-deterministic algorithm may produce different results because it uses randomness or changing execution paths. The second classification is by complexity. Here we ask how much time and memory does the algorithm need? Time complexity measures the number of operations. Space complexity measures memory usage. The third classification is by design. This is the central focus of this presentation. Here we study strategies such as divide and conquer, dynamic programming, and greedy algorithms. So, classification helps us understand algorithms from different angles, how they are implemented, how efficient they are, and what design strategy they follow. This slide shows complexity curves. These curves help us understand how an algorithm behaves when the input size grows. The horizontal axis represents the input size, usually written as n, pronounced n. The vertical axis represents the number of operations performed by the algorithm. The base case shown here is big O of 1, pronounced big O of 1. This means constant time. The algorithm takes almost the same time no matter how large the input becomes. Next is big O of log n, pronounced big O of log n. This grows slowly. Binary search is a common example. Then we have big O of n, pronounced big O of n. This is linear time. If the input doubles, the work roughly doubles. After that comes big O of n log n, pronounced big O of n log n. Many efficient sorting algorithms, such as merge sort, fall into this category. Then we see big O of n squared, pronounced big O of n squared. This grows much faster. Bubble sort is a common example. Finally, we have big O of 2 to the power n, pronounced big O of 2 to the power n. This grows extremely fast and quickly becomes impractical. The shaded area is called the danger zone. It reminds us that an algorithm may look acceptable for small inputs, but when the input becomes very large, inefficient growth rates become a serious problem. So, complexity analysis helps us predict performance before running the algorithm on massive data. This slide compares three core algorithm design paradigms: divide and conquer, dynamic programming, and greedy algorithms. The first paradigm is divide and conquer. The main idea is to break a problem into smaller subproblems of the same type. Then we solve those subproblems and merge the results. This approach often uses recursion. Merge sort and quicksort are common examples. The second paradigm is dynamic programming. Dynamic programming is useful when subproblems overlap. Instead of solving the same subproblem again and again, we store the result and reuse it later. This saves time, but it usually requires extra memory. Dynamic programming often gives a guaranteed optimal result when the problem has overlapping subproblems and optimal substructure. The third paradigm is greedy algorithms. A greedy algorithm makes the best local choice at each step. It chooses what looks best immediately and hopes that these local choices will lead to a global optimum. Greedy algorithms are usually fast and use less memory, but they can fail if the local best choice does not lead to the best overall solution. So the key difference is this: divide and conquer splits and merges, dynamic programming remembers and reuses, and greedy algorithms choose the immediate best option. This slide explains merge sort, one of the best examples of divide and conquer. We begin with an unsorted list: 4, 6, 8, 5, 7, 11, and 40. The first step is divide. We split the list into smaller parts. The left side becomes 4, 6, and 8. The right side becomes 5, 7, 11, and 40. Then we continue dividing until each small list contains only one element. The second step is conquer. A list with only one element is already sorted. So the smallest subproblem is solved automatically. The third step is merge. We now combine the smaller sorted list into larger sorted lists. At the bottom of the slide, we see two pointers, I and J. These pointers compare the first available elements of two sorted sublists. The smaller value is placed into the merged array first. Then the pointer moves forward. For example, when comparing 4 and 5, 4 is smaller, so 4 goes first. Then we compare 6 and 5. 5 is smaller, so 5 goes next. This process continues until all elements are merged. The final sorted list becomes 4, 5, 6, 7, 8, 11, and 40. Merge sort is powerful because it breaks a large sorting problem into smaller sorting problems, then combines the answers systematically. This slide shows why dynamic programming is useful. The example is the Fibonacci sequence. The Fibonacci function for 5 is written as fib of 5. It depends on fib of 4 and fib of 3. Then fib of 4 depends on fib of 3 and fib of 2. Fib of 3 depends on fib of 2 and fib of 1. Now notice the problem. Some values appear repeatedly. Fib of 3 appears more than once. Fib of 2 appears more than once. Fib of 1 may also appear repeatedly. In a simple recursive solution, the computer calculates these same values again and again. This wastes time. Dynamic programming solves this problem by storing results. Once fib of 3 is calculated, we save it. Later, if fib of 3 is needed again, we do not calculate it again. We simply return the stored value. This is called avoiding recomputation. So dynamic programming is especially useful when a problem has overlapping subproblems. Instead of repeating the same word, we remember previous results and use them again. The trade-off is that we use more memory, but we save a large amount of time. This slide explains two common ways to implement dynamic programming: memoization and tabulation. The first method is memoization, also called the top-down approach. We start from the original problem, such as fib of n, then we recursively move downward into smaller subproblems. Before computing a value, we check whether that value is already stored in memory. If the lookup value is empty, we compute it and store it. If the value already exists, we simply return the pre-computed result. So memoization follows the natural recursive structure, but adds memory to avoid repeated calculation. The second method is tabulation, also called the bottom-up approach. Here we start with the smallest known answers. For Fibonacci, the base cases are stored as 1 and 1. Then we build the solution upward step by step. The formula shown on the slide is pronounced as results.append open bracket results at I minus 1 plus results at I minus 2 close bracket. This means the next Fibonacci value is created by adding the previous two values. The main difference is this: memoization starts from the top and goes downward when needed. Tabulation starts from the bottom and builds upward until it reaches the final answer. Both methods use memory to improve efficiency. This slide introduces greedy algorithms using a coin changing example. The core logic is simple: sort the available options by maximum immediate benefit, then choose the largest possible option at each step. In the slide, the total amount is 98. The algorithm first chooses the largest coin value that can fit into 98. It selects 50. After taking 150, the remainder is 48. Next, it chooses 25. After taking 125, the remainder becomes 23. Then it chooses 10. It can take two tens, making the remainder 3. Finally, it uses one value coins to complete the remaining amount. The result is a total of 7 coins. This is greedy thinking. At each step, we do not look at all possible future combinations. We simply ask, what is the best choice right now? The hope is that by choosing the best local option at each step, the final answer will also be globally optimal. However, as we will see in the next slide, this hope is not always correct. This slide shows the main weakness of greedy algorithms. In the first example, greedy works well. The target total is 15 and the available standard coins include 10 and 5. The greedy algorithm first chooses 10, then chooses 5. 10 plus 5 equals 15. This is optimal. But in the second example, greedy fails. Here the target total is 15 and the available coins are 9, 6, and 1. A greedy algorithm first chooses 9 because 9 is the largest coin that fits into 15. The remainder is 6. But depending on the shown greedy route, the algorithm may continue with smaller choices and produce a sub-optimal path such as 9 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 that uses many coins. The better global solution is 6 plus 6 plus 1 plus 1 plus 1, which also equals 15 but gives a better result than the greedy path in that situation. This example teaches us an important lesson. Greedy algorithms are fast because they do not evaluate the entire problem space. But because they only focus on local decisions, they can become trapped in a suboptimal global solution. So, greedy algorithms are useful, but we must confirm that the greedy choice property is valid for the problem. This slide presents Dijkstra's shortest path algorithm as a case study. Dijkstra's algorithm is a greedy algorithm. Its goal is to find the shortest distance from one starting node to all other nodes in a graph. In this example, the starting node is A. The graph contains nodes A, B, C, D, E, and F. Each edge has a weight, which represents distance or cost. The greedy step is this: continually choose the unvisited node with the smallest known distance from the starting node. Then check its neighboring nodes and update their distances if a shorter route is found. For example, from node A, we can directly reach node B with distance 5, node D with distance 9, and node E with distance 2. Among these, E has the smallest distance, so the algorithm visits E first. From E, we can reach F with an additional distance of 3. Since A to E is 2 and E to F is 3, the total distance from A to F becomes 5. The table on the slide stores three things: the node, the shortest known distance, and the previous node. The previous node helps us reconstruct the actual path. For example, if F has shortest distance 5 and previous node E, that means the shortest route to F goes through E. This class algorithm is greedy because it always selects the nearest unvisited node at each step. But for graphs with non-negative edge weights, this greedy strategy gives the correct shortest path. This slide introduces one of the most important questions in computer science: P versus NP. First, let us understand P. P stands for polynomial time. These are problems that computers can solve efficiently using a step by step logical process. In simple terms, P problems are considered relatively easy for computers to solve. Now, let us understand NP. NP stands for non deterministic polynomial time. These problems may be very difficult to solve, but if someone gives us a proposed solution, we can verify that solution efficiently. So the difference is this: P means the problem can be solved efficiently, NP means the answer can be checked efficiently. The big question is pronounced: does P equal NP? This means if a solution can be checked quickly, can it also be found quickly? This is called the $1,000,000 question because it is one of the Millennium Prize problems. If someone proves it correctly, it would have major consequences. If P equals NP, many currently difficult problems could suddenly become efficiently solvable. This would affect cryptography, optimization, game theory, and many areas of science and technology. The diagram shows P inside NP because every problem that can be solved efficiently can also be verified efficiently. This slide explains NP hard and NP complete problems. An NP hard problem is at least as hard as the hardest problems in NP. More formally, if all problems in NP can be mapped or reduced to a problem in polynomial time, then that problem is NP hard. An NP complete problem is a special type of problem. It is both in NP and NP hard. In simple terms, NP complete problems are the most important difficult problems inside NP. They are important because if we find an efficient solution for one NP complete problem, then we may be able to solve many other NP problems efficiently as well. The slide also gives real world examples. The traveling salesman problem is one example. It asks, given several cities, what is the shortest route that visits all cities and returns to the starting point? Another example is integer factorization, which is important in cryptography. Modern security systems, including systems related to RC encryption, depend on the difficulty of factoring very large numbers. So these concepts are not only theoretical, they influence cybersecurity, route optimization, scheduling, and many real world computational systems. This final slide gives us a practical decision tree for choosing an algorithmic strategy. The first question is, can the problem be broken into smaller sub problems? If the answer is no, then we may need to use an iterative method or brute force approach. If the answer is yes, then we ask the next question: do the subproblems overlap? If the subproblems overlap, dynamic programming is usually a strong choice. We can use memoization or tabulation to save computation cycles. If the subproblems do not overlap, we ask another question: are local optimum choices mathematically guaranteed to give the global optimum? If the answer is yes, then a greedy algorithm may be suitable. Greedy algorithms are often fast, but we must be careful because local choices can sometimes lead to traps. If the answer is no, then divide and conquer may be a better strategy. We divide the problem, solve the smaller parts, and merge the results. This dysentery is useful because it reminds us that algorithm design is not random. A good programmer or computer scientist chooses a strategy based on the structure of the problem. So, to summarize the full presentation, complexity tells us how an algorithm grows, design paradigms tell us how an algorithm thinks, and computation limits tell us what may or may not be practically solvable. Algorithm design is therefore not only about writing code, it is about selecting the right strategy for the right problem. Before we end this lesson, let us step back and understand the bigger picture of algorithm design. Throughout this presentation, we have seen that an algorithm is not just a piece of code. An algorithm is a plan for solving a problem. Code is only the final expression of that plan. Before we write code, we need to understand the nature of the problem, the size of the input, the expected output, and the resources available to us. In real programming, many students think that if a program gives the correct answer, then the work is finished. But in computer science, correctness is only the first requirement. A good algorithm must also be efficient, scalable, and suitable for the problem. A program that works for 10 inputs may become useless for 1 million inputs. That is why we study algorithm design techniques and strategies. First, we studied the classification of algorithms. Algorithms can be classified by implementation, by complexity, and by design. Classification by implementation helps us understand how the algorithm runs. For example, a recursive algorithm solves a problem by calling itself again and again until it reaches a stopping condition. An iterative algorithm solves a problem through repeated steps, often using loops. Some algorithms run serially, meaning one step happens after another. Some can run in parallel, meaning many operations can happen at the same time. Some algorithms are deterministic, meaning the same input always gives the same output. Others may be non deterministic, where randomness or different execution paths can affect the final result. Second, we studied complexity. Complexity is one of the most important ideas in algorithm design because it tells us how an algorithm grows when the input becomes larger. We usually describe this growth using big O notation. Big O notation does not tell us the exact running time in seconds, instead, it tells us the growth pattern. For example, big O of 1 means constant time. The algorithm takes almost the same amount of work regardless of input size. Big O of log n means the growth is very slow. Big O of n means the work grows directly with the input. Big O of n log n is common in efficient sorting algorithms. Big O of n squared grows much faster. Big O of 2 to the power n grows extremely fast and can become impractical very quickly. This idea is very important in the modern world because we now work with large amounts of data. In artificial intelligence, big data, search engines, social media platforms, and scientific computing, algorithms often need to process millions or billions of records. In such cases, choosing the wrong algorithm can make a system slow, expensive, or even impossible to run. Then we discussed the three major design paradigms. The first paradigm was divide and conquer. In divide and conquer, we break a large problem into smaller sub-problems, solve those smaller problems, and then combine their results. Merge sort is a very good example. It divides a list into smaller parts, sorts those parts, and then merges them back into one sorted list. The power of divide and conquer is that it gives structure to a large problem. Instead of trying to solve everything at once, we solve smaller, manageable parts. The second paradigm was dynamic programming. Dynamic programming is useful when the same subproblem appears again and again. A simple recursive solution may solve the same subproblem many times, which wastes time. Dynamic programming avoids this by storing previous results and reusing them. This is why it is often described as remembering the past to improve the future. Memoization works from top to bottom, tabulation works from bottom to top. Both methods use extra memory, but they can greatly reduce computation time. The third paradigm was greedy algorithms. Greedy algorithms make the best immediate choice at each step. They are often simple, fast, and memory efficient. However, greedy algorithms must be used carefully. Sometimes the best local choice leads to the best global solution, but sometimes it does not. The coin changing example showed us this clearly. With some coin systems, greedy works well. With other coin systems, greedy can fail and produce a suboptimal result. So, before using a greedy algorithm, we must ask whether the local best choice is guaranteed to lead to the global best solution. We also studied Dijkstra's shortest path algorithm. This is a strong example of a greedy algorithm that works correctly under the right conditions. It repeatedly selects the unvisited node with the smallest known distance and updates the distances of neighboring nodes. This method is widely used in route planning, network systems, GPS navigation, and graph based problem solving. Finally, we studied the limits of computing through PNP, NP-hard, and NP-complete problems. This part teaches us that some problems are naturally difficult. P-type problems can be solved efficiently. NP-type problems may be difficult to solve, but their proposed answers can be checked efficiently. The famous question, does P equal NP, asks whether every problem that can be verified quickly can also be solved quickly. This remains one of the biggest unsolved questions in computer science. If it is ever solved, it could affect cryptography, cybersecurity, optimization, mathematics, artificial intelligence, and many other fields. So, what should we remember from this lesson? The main lesson is that algorithm design is decision making. Before choosing a method, we should ask important questions. Can this problem be divided into smaller parts? Are the same sub problems repeated? Can we store previous results to save time? Is a greedy choice safe here? How much time and memory will this algorithm require as the input grows? Is the problem practically solvable or does it belong to a very difficult computational class? When students learn algorithms, they should not only memorize names such as merge sort, Fibonacci, Dijkstra, or dynamic programming. The deeper goal is to understand the thinking pattern behind each algorithm. Once you understand the pattern, you can apply it to new problems. In simple words, algorithm design teaches us how to think before coding. It helps us move from writing a program that only works to designing a solution that works well. This is what separates basic programming from real computer science. So, whenever you face a new problem, do not immediately start writing code. First, analyze the problem, then choose the right strategy, then think about complexity, then write the solution. That is a real blueprint of algorithm design.